Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 8, 2026, about 3 days ago. It introduces a video understanding framework that slashes the average response length by roughly 3.3 times, reducing it from 149 tokens to just 44, while still maintaining state-of-the-art accuracy. The paper is titled VideoAuto-R1, Video Auto Reasoning via Thinking Once, Answering Twice. And as we'll see later, the results for both efficiency and reasoning capability are quite impressive. For those interested in the implementation, the authors have shared their code on GitHub. Figure 1 maps out the proposed framework compared to existing methods. On the left, panels A and B show that traditional models either inefficiently reason for every single query or struggle to learn a stable switching policy. Panel C introduces VideoAuto-R1, which generates an initial answer first. If the model is confident, it triggers an early exit to save compute. The examples on the right demonstrate this. For a simple perception task, like identifying a shirt, it stops immediately. However, for a harder physics problem, low confidence activates the reasoning chain to reach the correct solution. So, Table 1 provides the data that motivated this entire approach. Here, the authors compare direct inference against chain of thought inference across several standard video models. If you look at the response length column, you immediately see the cost. For VideoAuto-R1, enabling reasoning explodes the token count from roughly 18 to nearly 400. But crucially, looking at the accuracy columns, this extra effort often backfires. The red negative values show that on general benchmarks like VideoMME, performance actually drops with reasoning. It is only on specific, complex tasks like VideoMMMU, shown in the fourth results column, that the reasoning steps consistently add value, indicated by the green positive numbers. Well, Figure 2 outlines how the authors implement this adaptive strategy. On the left, Panel A illustrates the training process, where the model learns to output an initial answer, followed by a thinking trace, and finally, a reviewed answer. A composite reward function, shown at the bottom, evaluates both the initial and reviewed answers to ensure quality at every stage. Then, looking at Panel B on the right, the inference logic takes over. The system generates that initial answer and calculates a confidence score. If this score exceeds a set threshold called tau, the model exits early to save compute. If not, it triggers the full chain of thought reasoning. Alright, Table 4 shifts the focus to temporal grounding benchmarks, where the goal is to pinpoint specific moments in a video. The authors found that for these tasks, the initial prediction is usually sufficient, so the model defaults to the early exit mechanism to save compute. Despite skipping the full reasoning chain, the results in the bottom rows are strong. On the Charades STA dataset, the mean intersection over union, or MIOU, hits 60%. Similarly, on the ActivityNet benchmark in the middle columns, the model outperforms prior systems like VideoChat R1.5, achieving an MIOU of nearly 48%. Now, Table 3 compares the new framework against standard think-only reasoning models. In the response length column, the efficiency gains are striking. While the VideoAuto-R1 model averages nearly 390 tokens per response, VideoAuto-R1 slashes this to just 44. This stems from the adaptive strategy, shown in the bottom rows. For a perception task like M versus bench, the model triggers reasoning just 25% of the time. But for the complex VideoMMMU benchmark, that rate doubles to 51%, spending compute only when necessary. So, Figure 3 details how adjusting the early exit threshold impacts performance across different tasks. The x-axis tracks this confidence threshold, while the blue bars measure accuracy, and the red line tracks how often the model enters thinking mode. On the left, for the reasoning-intensive VideoMMMU benchmark, we see a clear correlation. As the threshold rises, the model thinks more, and accuracy steadily improves from roughly 57 to 59%. However, the VideoMME chart on the right reveals a different pattern. Here, forcing the model to think more, indicated by the rising red line, adds no value, as the blue accuracy bars remain flat. This confirms that for straightforward perception tasks, the initial quick answer is usually correct. Wrapping up, two main takeaways stand out. First, unconditional reasoning is often overkill for video understanding. Second, by letting the model decide when to think based on confidence, VideoAuto-R1 drastically cuts compute costs without sacrificing accuracy. This adaptive strategy offers a promising blueprint for more efficient multimodal systems. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.